So I'm sharing the screen right now, and this is an older file, and this is the software. So you can see here, let me show you step by step how we make it. So this is the first section sketch. So we have sketched a section, and if you remember the diameter of the cylinder that you tested for torsion in the lab, it was 1 inch. So we have made here a circle of radius, 1/2 inch. And you can see, I hope you're able to read the print here. If not, just let me know on the chat. I don't know how to. Okay. Let me open the chat. I hope you are able to read what is. Okay, great. So you can see here. Okay, great. Thank you. Thank you, Zila. Yes. Now you can see extrude here, and if you have used uh, Inventor or SolidWorks or something, then you are familiar with what is extrude. So you create a section and then you extrude that section. So that extrusion depth was so the extrusion depth was 11.28 inches, and this was the length of the rod from end to end that you tested for torsion. So now this is the rod. Okay, you can see the rod here, or this is a model of the rod. So the next step is to create partitions. So as you can see, maybe I'll just explain what's the reason for doing that. Okay. So the reason for partitioning the rod like this is so that we can mesh it in this way. So last time we very briefly discussed what is a mesh. So the rod is broken up into very small parts, and you can see that each of those parts is like a wedge. And the reason we have broken it up into wedges is so that even after twisting, we can see now here are the mesh shapes. So after twisting, we want to see how far our assumptions are true. So if you remember, we said that after twisting, these planes, they remain planar and they remain straight, right? So that means they. Oh, Ali, you can just mute the microphone at your end. So these lines that you see, we want them to remain straight after twisting. That means whatever assumption we made, that is satisfied. And these longitudinal lines, we want them to remain straight after twisting. So if you remember, this was in the elastic theory of torsion, these were the two assumptions. And if they are true, then the theory what we developed is applicable here. And okay, so that was about mesh. So that we can break it up into wedges, we need to do this partitioning like this way. Okay. Uh, oh, uh, excuse me for a moment. Okay, sorry. So that's why we did the partition. Okay, so that we can have this kind of mesh with circular symmetry. So this is the main reason that we want a mesh with circular symmetry, because initially our part is symmetric around the longitudinal axis, right? It's a cylinder. Next step, you can see here materials. So here in the Abaqus, you can see there are different modules, part, property. So material comes under property module. Okay. So we have defined a material here. So you see we have a Young's modulus and Poisson's ratio. So this one we have assigned, do you remember we calculated shear modulus from our experiment? And so based on that, so here is our shear modulus. And actually let's B1. Okay, we set Poisson's ratio of 0.25. We can adjust that. Now, here is our elastic modulus based on the shear modulus. So if you, all those who are in the theory class, you may remember this relationship. So you remember this, right? Now, we had derived this using the Mohr circle to show how to show the equivalence between axial or axial deformation and shear deformation. Okay. Anyway, but we use this relationship to obtain the E. So you can see G times 2 times 1 plus nu. So we got this E value, and if you all might have noticed in Abaqus, there are no preset units, and I think somebody's microphone is on. Please could you all mute? A lot of, I'm not sure who. Okay, maybe it's, yeah, somebody's microphone is still on. Okay. Uh, okay. Anyway, now here is E, and so when we go to the materials, this is where we enter it. Okay, you can see the value is something different. So let's enter the correct value: 4577375. So that is our E. Poisson's ratio is that much. Okay, so we assumed it to be an isotropic material. So the bar was made of some kind of iron, and it's not a bad assumption for that. Okay. Now, uh, the next step is to assign the boundary conditions and the loads. So what we mean by that is, let me show you. So you can see load 1. So we have applied here, so it says CM3. Okay, so what is this CM3? So we have applied it to region set 7. So let me first show you what is set 7. So in the sets, oh, okay, that is only set 4. Just a second. Okay, so set 7 is this reference point. So again, we don't want to go too much into detail, but very briefly, the way we are applying this moment is, now you can see here constraints. So constraint 1. So this is kind of like saying this reference point here is coupled to this pink surface. That means whatever condition we apply to the reference point is transferred to the entire surface. Okay. So this is the way we apply a twisting moment in the software Abaqus. Okay. So let's see where is the load. So double click. So it is that much. Okay, 3,520. And if you remember, uh, I think this was the maximum twisting moment that you applied. I hope, I don't know if any of you has your torsion lab report still with you. If you have, you can pull it up so that I know there were two types of samples. One was small, one was large, but whatever we are doing, that should kind of roughly conform to. Okay, so here is the 3520 pound inch. By the way, you may have observed that there are no units here. So it's our job to make sure that all the units are consistent. That means all the loads should be in pounds and all the dimensions are in inches. And not should be. All the loads we give in pounds, all the dimensions we give in inches. So therefore, whatever Young's modulus we give should be in PSI. We cannot give some other unit. If not, it will be inconsistent. So this is another point. Okay, so now let's see the boundary condition. We need to adjust a bit. So here we have defined Ncaster. So what is Ncaster? U1, U2, U3, UR1, UR2, UR3, all are 0. Okay. So I will tell you what this means. Now U1, see, remember 1 refers to x-axis, 2 refers to y-axis, 3 refers to z, okay? So actually, wait a second. I didn't want to, okay. So we have fixed everywhere in along this clamp, and what we want to do is we well, for now let's take it like this. Now you will see a bit of the result which is not realistic, but we will see next how to fix that. Okay, for now take that as the boundary condition. That means we are fixing one end of the bar, and at the other end we are applying a twisting line. Okay, now let's, that's what we created. Now this is job. So what does job mean? Job means that you defined all the material properties, you constructed your geometry of the model, you made a mesh, you assigned the loads and boundary conditions. So everything is completed. So now you go ahead. We can. Uh, this is okay. So right click on this and submit. Okay. So when you submit, okay, overwrite, just say okay. So you can see here that it is going to solve. So what is it solving? Last time, if you remember briefly, I explained to you about finite element. Uh, I hope you all remember. So what it means is that it is difficult to predict the behavior of the full rod accurately, but we can do that somewhat accurately for each element. Okay. Now I'm explaining in a very crude way. We are actually solving the okay, you know what is the governing differential equation for equilibrium. You remember that. I hope you all remember. If not, just to refresh. Okay, maybe I don't have here. Maybe I'll just show you in the text. That may be better. We did discuss it in class. I hope you remember. Okay, so So this is for 2D, but we wrote down in the class for, okay, I know not all of you are in the class, but we wrote down the differential equations for equilibrium in the class for 3D, if you remember. So these are the equations that are being solved in the software, okay? So once it is solved, let's go check the results. So this is the undeformed bar, and whoops. So, okay, so here, okay, so here something is off. Ah, so I understand what's happening. Let's go edit the boundary condition. So as you can see, I thought it was, it really applied the boundary condition everywhere. Only this end is fixed, but it has fixed so many points. So let's uh, let's just do one thing. Let me reopen this one. Okay, so now you can see the correct boundary conditions. They are all fixed here, okay? So now when we submit, let it run. Okay, completed. Result. Okay, so the artifact you can see is that this end, if you look at it in the YZ view, this end has expanded a lot with respect to this end. So that's because we artificially fixed this end, and that's why you see this expansion. This is kind of exaggerated in the sketch. It actually does not do this much. And uh, excuse me for a moment. Okay, sorry. Now, what are the stresses we want to observe? And what are the deflections that we want to observe? So first, let's look at, okay, this is one misses stress, but let's first look at shear stress. So S means stress. Now, if we want to see the shear stress on this plane, what will it be? It will be S31 and S32. So did you get why it is S31 and S32? Because this is z-axis, right? So therefore this cross-sectional plane, this is z-plane, okay? This is z-plane, so that number is 3. And then we want in the direction y and x. So now if you see S32 or 23, okay, so you can see that it is much higher in these regions, and here it is negative. And if you look at 1, 3, and so it is like that, okay? So did you understand these 2 points? That why you will see only 1, 3 and 2, 3. Because remember, how are the stresses in torsion? So they go, the shear stress due to torsion goes in a circle, right? That is the shear stress, remember, due to torsion. So in the y direction, you will focus on those. In the x direction, you will focus on those, okay? So that's what we are seeing here. 1, 3 and 2, 3. Now, okay, what to do? First question for your report. Here is the UR, okay? Now, all of you can take a snapshot of this screen. Minimize the chat. You can take a snapshot of this screen.
What's the question again?
Yeah, I will tell you the question. First, take a snapshot of the screen. Okay, so now you compare. Oh, that line is made by somebody. Okay. You can compare the angle at this angle of twist at this end at the outermost face. What is the angle of twist? 0.2338 radian, right? So compare that with the angle of twist which you got in your experiment. So you must have written down in your experimental data for a torque of 3520 pound inch. So if you don't have that exact number, then you need to calculate. Okay, so you can calculate the angle of twist by multiplying the twisting moment by flexibility, torsional flexibility. Okay, so you can get the angle of twist. So compare that hand calculation to this number. Okay, to this number. And
could you go back to the other screen?
Okay. I forgot what was the other screen. Oh, do you mean this this data? This data you all have already, so you don't need to use this data. You can use the data that you collected for your cylinder in the lab.
This is the data from the lab that we, that we performed in class, right?
That's right. Yeah. So make sure that I think there were two cylinders. So one of them, I don't remember. One of them was only half a foot long. Make sure you're using the data for the cylinder that was about 1 foot long. Okay. Don't use the data for, and the other smaller one was only ½ inch in diameter. I don't remember exactly which group did the large cylinder, which group did the small, but use the data for the large cylinder. Okay? And compare the angle of twist. So that is the first question.
Can you send it to us in email?
Okay, I can do that, but you can write it down now as well. Okay, let me do one thing. How about I type in the chat?
Yeah, that's in chat.
Or that's fine. Email is okay. So I'm writing the email. So first question. Calculate the angle of twist. Calculate or look up data of 3520 compare this to the outermost face in Abaqus. Now, next one. Now look at, no, okay, first thing, please ignore this expansion at this end. We will fix that shortly. But ignoring that, now take a snapshot of this picture. That's okay. Yeah, take a snapshot of this picture. And also take a snapshot of this picture. So second question is, by looking at the, okay, there is a question on the chat. By looking at the mesh boundaries for the deformed and undeformed cylinder, comment on whether the linear elastic theory of torsion is applicable here. Okay, that's the second. Now let's see, somebody asked, oh, can you go back to the first one? Okay, sure. So William, I'm going back to the first one now. Okay. Not this one, is it? Okay, sure. Okay, so those were the first two questions. Next is, now let's see S12.
So what are the different colors meaning?
Okay, so the colors are nothing but a contour plot. So they are just used to indicate red means high value, blue means low value or high negative value. That's all. It's just a legend.
Okay, and the values are the angles of twist for each part of the rod?
Value, okay, when I selected UR and UR3, so these are the angles of twist, okay?
Okay.
Now I'm selecting stress, S, okay? Now I'm selecting the stress S, and this is, just ignore this one basis. Let's just look at, so just a second. Okay, so look at S13, and you know how to calculate the shear stress. So take a snapshot of this. Okay, you took. So now next question is, calculate the maximum shear stress in the cross section of the bar for the applied twisting moment of 3520 pound-inch. Compare this to the maximum magnitude of S13 from the simulation. Okay. And compare means comment also. Okay. Just a second. Let's see if we can choose polar. Okay. Okay, so till now these questions all of you have written down. Now let's do a bit of changes.
No, I didn't written. I didn't.
Okay. So I'm sending.
So
I will send, okay? I will send this.
Yeah, that's it. Okay, thank you.
So let's change this to cylindrical. With okay, so let's first fix this kind of expansion. Let's go to our model, and in the boundary conditions, instead of doing this encastre, let's do let's suppress this. Let's make a new boundary condition with displacement and rotation. Select region. So let's select. Oh, I think Joshua is trying to ask something, but I don't know what. Okay. So let's no, actually let's just select this point. For this point, we don't want it to move. U3 is fine, U1, U2 not fine.
Are the U's just the points on the cylinder?
I'm sorry, what's the question?
Are the U's just the points on the cylinder?
No. U is displacement.
Okay.
U1 is displacement in x direction. U2 is displacement in y direction. U3 in z direction. UR1 is rotation about x-axis. UR2 rotation about y-axis. UR3 rotation about z-axis. Okay. Now UR3 we want to fix. Now UR1 also we want to fix. Okay. We fixed everything here only at this point. Now for the rest, we will define another boundary condition. That is this. Okay. For this one, let's give U1 is fine, U2 is fine. U3, let's fix. Okay, let U3 stay. Actually, let's fix this. So now let's try to rerun. So what we have done is, okay. So there is something not okay with the number 3. Yeah, I should fix U3 actually. So now it should be fine. Because it's not allowed, that face is not allowed to twist. It's still, okay, it's still some instability. U1, U2 are allowed to okay. Let's do for BC2 only U1, U2, U3. So that now it should be. Okay, so it's still unstable. So U3 should be fixed too. It's fixed. Okay, so I think the one I need to edit is VC3. Actually, maybe we can. Should be okay. Okay, so this expansion error you ignore for now. I will fix that, but please answer these 3 questions only. I hope you took the screenshots.
Okay.
Okay, so you got those. Now, now let's see the other simulation for the tensile test. Okay. Let's open that file. Okay. So now let's first check make sure this model is running. Yeah, it is running. Let's see the results. Okay, so that's fine. Okay, so here also we will do some numerical comparison with our hand calculation. So again, let's just go through what is the part we created. So here is the section that we sketched, and you all remember that this one is just like the aluminum section aluminum sample that we tested in our experiment 2. Now there are some partition cells. So there is partition cell 1 and 2. So this is a partition cell 1, this block, and this block is partition cell 2. And the reason we defined them is so that we can fix one of them, and then the other one we can constrain to move as a single block. That means it is as if we are somehow in the simulation, we need to give the condition that this block is held inside jaws, so it should have 0 strain. It cannot stretch. So the way to give that condition in a simulation is again using constraint. So you can see that this whole thing is tied to this reference point. So whatever condition we give for the reference point, it is also, it carries over to this entire block. Okay. So again, to make all of this, it will take some time. So we are just doing like a demo lab. So I'm just showing even I made much earlier. I'm not remaking anything. Okay. Now let's look at boundary conditions. So again, we used N-cast means this whole bottom block is completely fixed. So if you remember, in the experiment, the bottom block was completely fixed, right? So you remember that. Now, is there any? No. Okay. Now, let's see the load. So the load says that the load applied is to this reference point, and whatever is the motion of the reference point, the same is the motion of the entire block. That means we are restricting it to a rigid body motion. Okay. So the first question is for this simulation is what is the purpose reference point the top part of why is the reference hide what conditions of the experiment are we? Okay, that's the first question. Then second question is, so what are the boundary conditions the bottom end of the okay. So then the load, let's say how much is the 3,400 pounds. Okay, so now let's see what is the type of material model we gave.
Professor Nathan,
Yes.
the reference point is the fixed point?
This RP is the reference point.
Yeah, but is it fixed?
No, it is not fixed, right?
Okay. It's the other part at the bottom that's fixed.
Yeah.
Okay.
The reference point is tied to this rectangular block. Okay. Do you remember this? You can take a snapshot of this constraint. All of you can take a snapshot so that it will help you to answer the first question. Okay?
Okay.
Okay. So now okay, material we just gave elastic, okay? So I will, if we have time, I will also show you the case for the plastic deformation. But for now, let's say elastic. So the Young's modulus, if you remember this value, 10 million psi, it is what you calculated. Actually, it is 1 million here. But if you remember, this was because in the okay, maybe this is the next question. I will not tell the answer. So this is actually from the lab, and I hope you are able to remember that. So in the lab experiment, why did we get elastic modulus close to 1 million psi instead of 10 million psi. That is the experiment. Question. I hope you all remember why that happened. What is it about the lab equipment? So you remember. Okay. So here is the Young's modulus and
Actually, I didn't remember.
Huh? Okay.
Please remind us.
Okay. So if you don't remember, see, there is a load cell and then there is an extensometer, right?
Yeah.
Yeah, the load cell is fine. It's calibrated well. The extensometer is off by a factor of 10. That's the reason.
Okay.
Now, anyway, let's see the simulation after you run. So you applied this load at the reference point, then that whole block moves along with the reference point. So we check the results. Okay, so you can take a snapshot of this. Let me move these views. Viewport. Okay, you can take a snapshot of this. No, just wait. Let me change the misses to now. You all tell me in the chat what stress I should choose here. 1, 1, 2, 2, 3, 3. What is the stress that you calculated in the lab? You can tell me in the chat window. Which one should I choose? 1, 1, 2, 2, 3, 3. You already learned in the theory class what are the, how do you define 3D state of stress? The stress that we defined in the lab, force per unit area. So that is which one? Is it 1, 1, 2, 2, 3, 3? Which one is it? You can tell me.
1, 3.
Oh, I'm sorry. Actually, today I have just a suggestion to you. I have only one screen right now. So if you send private message in the Zoom chat, still everybody can see it, okay? Because my screen is shared. So I think everybody is able to see. So
No, I can't send it to you privately.
Yeah, okay. So no, it's not. No, Alidia, of course it is not 2, 3. 2, 3, is it normal stress or shear stress?
I say 1, 3.
Ali, again you are giving me shear stress. How can it be 1, 3? What is the stress you calculated in the lab? 1, 3 is shear stress, right? Or
Yeah.
2, 3 is shear stress, right?
Mm-hmm.
So it's not what we calculated, right? What we calculated for this experiment was normal stress, right?
Mm-hmm.
So which one I should choose? Here, like I should choose which one? 1, 1, 2, 2.
Normal stress. I think 1, 1.
No, see, where is x-axis? X-axis is in this direction, right? X-axis is in this direction.
Okay.
So stress S11 will be on this plane here. So is there any stress on that plane? No, right? So which is it? Okay, so that's right, Bishwa. It's S22, but then okay. So let's take S22. So it will like. No. Okay, maybe you got confused. So nothing about the numbers. Okay. So what we are asking is which is the stress? Okay, maybe you didn't see this coordinate system. I hope maybe you all did not notice this coordinate system sitting here. Y is going that way, X is going that way, and Z is coming out that way, right? Okay, I guess you, okay, now after you see that, you can tell that it's S22. Okay, so I guess you all didn't notice that. Okay. Okay, so, no, by the way, please don't hesitate to give any answer. Whether it's a right or wrong, that's not we are trying to understand. So it's not, even I'm trying to learn the subject. So we are, all of us are trying to learn. So there is nothing wrong or in giving incorrect answer. So, but main thing is that in the end, we all understood what's going on. Okay. So this should be S22. And now is it clear why it is S22? Okay, maybe let me draw a figure here that may. So okay. So the area on which we are looking for the stress, or the area on which we can, is that area, right? Is that yellow area. So if you look at the axis there, so this is y-axis, this is x, this is z, right? So this normal stress on this area must be sigma yy, right? So we are, that is sigma 2, 2. So is it clear now? So you can, yes, okay, great. This, yeah, that's the main thing that we understood what's going on. Okay. Yeah, please, without the discussion, we won't move anywhere. I mean, you also may be right where you are, I also will be. So if to move ahead, we must discuss. Now, all right, so the question is explain. Next question is explain the stress distribution of stress 2 sample. Okay, that means why is it 0 in some places, uniform in some places, and very the gradient in some. That's the next question. Now, to answer that, you can take a screenshot of this screen if you haven't taken already. Okay, now take also a screenshot of so the total width is 0.54 inches, okay? So the width of the sample is 0.54 inches and the thickness of the sample is 0.128 inches. So please note down the numbers. The width of the sample is 0.54 inches and the thickness is 0.128 inches. Okay. Now compare from the previous, so from the contour plot of the S22, what is the stress in the red area? How does this compare to the calculated stress for an applied load of 3400? So let's check that the applied load was, yeah. Okay, so that's the next question.
Dr. Nathan, I have a question.
Yes,
It's a little off topic. So is only the torsion lab considered the final, or is the torsion and the tensile considered the final?
Let's make this lab is the torsion and the tensile.
Could you repeat that?
Both for this today's session.
Okay.
Both the same, because I know last time we did something, but we didn't really have the software to see anything. So.
Okay, thank you.
Okay. And actually it is not too big, so it's 2.8 GB. So if any of you have a little more space on your laptop, you can very easily install this. If you installed and if you want me to send these files, I can send you. Okay.
Professor
Must
Nathan,
submit lab next week.
Yes. No lab next week, but there is a final on the lab. Oh, can you say the thickness? Yes, I'm sorry. Thickness is 0.128 inches. 0.5. Let's make sure of the thickness. Yes, okay. But like we discussed, there is a final for this lab, and I will send out the final. So, of course, it is not an experiment or anything, but it will be based on the experiments that we did in the lab. Okay.
So in the email where you said the final lab was the torsion lab.
Yes.
So were you referring to, when you said final lab, were you referring to like it was going to be our last lab for the semester?
Yeah, today is our last lab of the semester.
Okay, so on top of this lab, we have an additional final. Like this isn't the final grade.
No, we have final exam. So of course, exam I will email. You answer the exam and email it back to me.
Okay, thank you.
Okay.
So when is it due to submit this lab?
This lab you can submit by next Tuesday.
Okay, thank you.
28, yeah. So
that's just a one-page report, right?
One page, and not even one page. You just write the answers to these questions.
Okay, great.
So, okay, then the other thing that we want to notice, it's only the elastic. Yeah, here this is all we can get because it is only a elastic simulation. So if you look at the plastic strain, so E is elastic strain. So it doesn't even have any plastic strain. Now, okay, now these are all the questions that you need to answer. Now, just for your information, I will also show you the simulation of the simulation for the plastic deformation. Okay, how we can do that. Send this out. Okay, so this is all that you need to send for today's lab. Now, I will just show you another. Oh, so let me also show you the plastic deformation. So this was from a while back that we did. Oh, so this is one of the previous students. Oh, so the software has crashed. Just a second. Oh, I'm just curious to know, did anybody try after that to install Abaqus? You can tell me, just you can tell me with your microphone, no need to chat. Anybody has tried? No. Okay, that's fine. Okay. All of us are very, very busy. Okay, yeah. So this is, if you remember, this is to simulate the threaded sample. And now I will show you here. So maybe no questions from this one, but just to show you. So here is a material that we defined, aluminum, right? So we have defined Young's modulus and Poisson's ratio here. But then, if you see, we also defined some plastic properties, that is yield stress, and we defined another yield stress here along with the plastic strain. So this is because we are trying to model the material behavior as elastic and elastoplastic with isotropic hardening. That means the stress strain, uniaxial stress strain graph goes like that. Okay, this is the yield point. Of course, the actual material goes, but we model it as a sharp point there. That is much easier to model. So that's why we give this point and another point, so that Abaqus can interpolate and form this line. Okay. Okay. So once we give that, what extra thing do we get? So let me show you that. Again, you can see that there is a big advantage here whenever you're designing anything. Before you make your design, you can already check if this is safe, and then what are the stresses for your applied loading and so on. By the way, nowadays, even in Autodesk Inventor, SolidWorks, I think all of these have a finite element, uh, what do you say, module embedded. But of course, that is kind of simplistic. It is not, what can you say? It is not dedicated for finite element, but it's there in most of the software. Okay. So what I was saying is now in addition to E, you can see here PE. So that is plastic strain. So you can see here is the plastic strain. Okay, here now the applied loading, the applied load we applied is 6,000 psi stress. So what is the, let's go back, what is the yield stress of the aluminum in the material? 54,000. So we are somewhere in between. So we have a bit of plastic strain here. Okay. So if you apply a bit higher load, so let's go to the load, and instead of 56, let's do 66. Before that, let's see if we have any damage here. I think we didn't put damage for this. No. No, I think we haven't put damage here. But anyway, you could see a plastic strain, right? So let's increase the load a bit more, maybe that much. And now let's see how it looks. So we are going well beyond the yield. Yeah, so you can see, we don't see any big difference, but just more plastic strain, okay? So if you want to see, I know in one of the models I showed you necking. So if you want to do necking, then in the material model, so you see the material model. So you just now we put only elasticity and plasticity, okay? So if we want to observe even the damage, then we need to use one of these, okay, damage model. So once we do that, we can start observing necking, okay, and also fracture too, okay. So we can do the entire simulation, but we are not doing it today, okay. So I think that's all. It is just, okay, let's see the question. Oh, okay, but, oh. Okay, I'll just enter my phone number in the. Okay. So if you have any doubt later on, you can call that number. Okay. Maybe morning is good than now. Okay. So, okay. So I think this one was just to give kind of introduction, and I know you don't have the software Oh, William has put an arrow there. Okay. And we didn't really do the simulation, but just so that you have some idea what we do. If you know the geometry, if you know the material properties, then you can simulate it. Okay. Okay. So I hope. So this is the last lab. I hope that we all of us, me too, we learned something from the experiments, and so I will all the best for the final exam, and you can email it to me once I send it. Okay. Okay. So please let me know if you have any more doubts, and then we will end the meeting.
Dr. Nathan, what day are you going to send our final exam?
Okay. So I will send 2 dates.
Okay, and what day is it due?
Due after 1 week time.
Okay, thank you.
Yeah, I will send now.
Okay, thank you, Doctor.
Yeah. Okay. Okay. So see you. I will end the meeting now. Thank you.
Thank you, Professor.
Thank you.